Welcome. In this session in linear data analysis, we'll explore the use of the SVD, or singular value decomposition, for a non-square matrix. A non-square matrix doesn't have eigenvalues or eigenvectors, but it always has a singular value decomposition. Let's switch to MATLAB to conduct our little exploration. Here, we'll use the matrix which has a first column of 1, minus 1, 2, and a second column of minus 1, 1, 0. We can see that these columns are linearly independent, and that implies that this matrix is rectangular and full rank. And because it has more rows and columns, sometimes we call this a tall, thin matrix. Although I would say that 3 and 2 isn't very tall and isn't very thin, but that's a common linear algebra use. This doesn't have eigenvalues, but it does have a singular value decomposition. So when I use the MATLAB built-in function SVD, what I get is this, is U3 is an orthogonal matrix, and that means that each of the columns are mutually orthogonal, the dot products are 0, and each of these columns has a unit length. And here I'm displaying it only to 2 decimal places so that we can easily understand it. The singular values are approximately 2.61 and approximately 1.08. So in this case, they're fairly close numerically. That is, they're both single-digit numbers. And then this is the right singular matrix. Let's make an observation here. This matrix has vectors of size 3 for its columns, and there are only 2 of them. That implies that this matrix has a column space that it has size 3 vectors, but it's 2-dimensional. How do I know it's 2-dimensional? It's because these are non-zero and they're not multiples of each other. So they're linearly independent. So the columns of this matrix span a 2-dimensional space in 3D. What's a basis for it? Well, we know that we could simply take, because these are non-zero vectors, we could take these as a basis. And from the singular value decomposition, one of the definitions of a best basis comes from the left singular vectors of the singular value decomposition. So what we do, this is actually algorithmic, is we count off the number of non-zero singular values. In this case, it's 2. And for each non-zero singular value, the corresponding left vector is a basis vector for the column space of the original matrix. And here we can see that this is approximately 0.5, 1/2 minus 1 over root 2, and then likewise here. So these don't have any instant physical or instant intuitive meaning, but they are, in a sense, the best basis that we could come up with. This doesn't have a singular value that corresponds to it. This is a curious kind of vector for us because it's in the orthogonal complement of the column space of this. And what we mean is that if we put any 2 vector in, if we multiply A3 by any size 2 vector, we will never get a multiple of 1, 1. And so this vector, this third left singular vector, is a basis for the complement of the column space of this. That can be a difficult concept for us to understand, but it's something that comes out of the singular value decomposition. For this particular example, we don't have a lot to observe out of the right singular matrix. Next, let's try a rectangular matrix. This is sometimes referred to as short wide because it has more columns than it has rows. And in this case, it's rank deficient. We can see its rank deficiency because the second row is a scalar multiple of the first row. That is, it's the negation. Another way to look at it is we could look at the first column of A4, and the second column is a scalar multiple of the first, and the third column is also a scalar multiple of the first. So what we could do from this observation is say that the column space of A4 must be size 2 vectors, and it's a 1D space in 2D. So that's what we can observe from the structure of A4. Now, let's compute the singular value decomposition. When we do that, what we see is that the singular values are now 3.46 and 0, and because it's rectangular, that's where we stop. So the rule is that we count up the number of non-zero singular values, and that gives us the rank of the original matrix. Here there's only one non-zero singular value, and that tells us that there is that the original matrix, in this case A4, is rank 1. What is a basis for that column space? Well, from the singular value decomposition, it would be the first column of the U matrix, or the left singular matrix. So any multiple of this first column is a basis, and minus 1, 1 would be a basis for the column space of this original matrix. The next vector is associated with a 0 singular value, and that implies that this vector, the second vector of the left orthogonal matrix, this is a basis for the complement of the column space of A4. That is, these are the vectors that if you take any 3 vector and multiply A4 by that size 3 vector, you will never get a multiple of 1, 1 coming out. Now, let's turn to the right singular vectors. A rule is that any 0 singular value, the corresponding column in the V matrix is a basis for the null space of A4, of a matrix. And that means that this vector, minus 0.9, minus 0.2, 0.4 to 1 decimal place, that is part of the basis for the null space. We then would take any columns that in the singular matrix are to the right of this, and those are also part of the basis of the null space. So here, the basis of the null space is the second right vector and the third right vector. Any linear combination of these will work out to be in the null space of this original matrix A4. So this is an example of the richness of the singular value decomposition.